QP and QC, which is called the reaction quotient. Now, reaction quotients will help us to predict whether the reaction is going forward or is it going reverse, all right? So, which means it is related to, of course, to the equilibrium and to the concentrations that are present in there. So, reaction quotients, the interesting thing is, of course, you can take out the gases or the materials at any time, okay, during the reaction. The QC expressions for equations are written exactly the same way as KC expression, but let me go ahead and do that here for you again. So the first problem is write the QC expression for the following reactions. That's my wonderful shorthand for reactions. So 2NO2 gas to give 2N2 and then oxygen, nitrogen and oxygen. So QC, we don't write KC anymore because KC is usually for equilibrium. QC is for reaction quotient. And so then products, which is then N2O2, and N2 is going to be squared because the coefficient is 2 there, and then over N2O, which is also going to be squared. So you can see the QC is the same way as KC would be set up. All right, so the next one then is hydrogen fluoride, aqueous, and dissociating into hydrogen ions and fluoride ions. So setting up the QC for this is the products, which is hydrogen ions and fluoride ions over hydrogen fluoride. Again, because this is aqueous, you have to write that also. The third one here is methane plus H2S, which is hydrogen sulfide, to give CS2 gas and then hydrogen gas. And so the QC for this one is CS2, hydrogen to the power of 4, because that's what the coefficient is for hydrogen, and then methane, which is CH4, no coefficient, and then H2S, and the coefficient here is going to be 2, okay, or it's going to be raised to the power of 2, because here is the coefficient. Okay, so that is how you solve for QC. That's the setup, okay, which means it's the same thing as KC. Anyway, so how does it matter for us, okay, what the QC is? Here is how it happens. So if QC is less than KC, then equilibrium moves right, which means products. Okay, so QC is equal to KC is when you have equilibrium, so which means the reaction is not really moving anywhere. And then when you have QC, which is going to be more than KC, then at that point the equilibrium moves left, okay, which means to the reactant side. Now the left and the right thing here makes perfect sense, because if you're looking at QC to be a large number, it means that the products are more than the reactants, and if the products are more than the reactants, then your equilibrium will be shifted backwards to fix that. Okay, so just because you have a reaction doesn't mean it's always going to go forward. Let's look at a problem for QC. It's calculated the same way as KC, as I said in problem number 1. So KC for nitrogen plus hydrogen to give ammonia is 1.2 at 375. What is the direction of the equilibrium if the concentrations of each component is as follows? And hydrogen, nitrogen, and ammonia are given to us. So all we have to do then is set up the QC for this. So QC is equal to, ammonia is our product, so NH3, and that's squared, and N2, and that is only 1 mole, and hydrogen, which is 3. Okay, so it's cubed, and so this is equal to, and then you plug in all the concentrations here. Ammonia is 0.48 divided by nitrogen, which is 0.60, and then for hydrogen, which is 0.76. Don't forget to cube this, and your answer is 0.87. So then you compare this value to the KC value, which is the 1.2 that's given over here. So QC is less than KC, because QC is 0.87 and KC is 1.2. So if QC is less than KC, equilibrium is going to the right. Okay, which means that you have less products in there. That's why your QC value is less. So that is our answer right there. Okay. Okay. Third one. For the reaction hydrogen sulfide plus iodine, this is I2, to give 2 hydrogen iodide plus sulfur as in a solid, the Kp is given to us at 60 degrees Celsius. Which gas will decrease in pressure? And I took this problem just to show you that you can work with Qp just like you'd work with Kc. Okay, so it's the same kind of thing. Qp, Qc, Kp, Kc, they're almost the same things. Okay, so here we're going to set up for Qp instead of Kc. All right, so our answer is going to set up for Qp, which is pressure of hydrogen iodide, which has a coefficient of 2, so you raise it to the power of 2. And then at the bottom you have pressure of H2S. And this one, by the way, my terrible handwriting, this is a solid. Okay, the iodine here is a solid, and so that does not go into the equilibrium expression. I know, I have beautiful handwriting. Okay, and then we go ahead and calculate the Qp for this, and that is 0.0010 squared divided by 0.010, and answer is 1.0 times 10 to the negative 4. 10 to the negative 4, compare that to, which is, this is Qp, and Kp is 1.34 times 10 to the negative 5. So Kp is smaller. Kp is less than, it's smaller than Qp. Okay, or you can say the other way around, is that Qp is greater than Kp, however you want to. And if Qp is greater than Kp, then your reaction is going to go back. If it is going back to the reactant, the pressure of H2S will increase. H2SP will increase. All right, so that is what your answer will be like then. All right, so pressure and concentrations, they all work the same way. So don't get too confused there. You don't have to convert Kc into Kp unless you're not asked to do so. Okay, so don't increase your own work.